Hello, in this lecture we'll answer two questions. In the first question we find out the area of this green shape, and in the second question we find out the area of this square ABCD. So we start with the first question. In the drawing we have a circle that is described by this triangle ABC. In addition, we know that side AB of triangle ABC equals to 6 units in itself, side AC equals to 7 units in itself, side BC equals to 9 units in itself. Again, our task is to find out the area of this green shape. So first of all, we define the size of this angle ACB as theta. And we implement the law of cosines in this triangle ABC. Repeat quickly on the law of cosines. The law of cosines is true in any triangle, so this is triangle ABC that could be any triangle. This triangle ABC, side AB equals to A units in itself, side AC equals to B units in itself, side BC equals to C units in itself. This is again BC, this is equal to theta degrees in size. According to this law, the law of cosines, this triangle ABC, the following equation is true, that cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. So we can actually implement the law of cosines in this triangle ABC. According to the law of cosines in this triangle ABC, cosine theta equals to AC square plus CB square minus AB square over 2 times AC times CB. Again, cosine theta equals to AC square plus CB square minus AB square over 2 times AC times CB. So write it down. Cosine theta equals to AC square plus CB square minus AB square over 2 times AC times CB. Again, according to the law of cosines, this triangle ABC, cosine theta equals to AC square plus CB square minus AB square over 2 times AC times CB. So cosine theta equals to AC square. AC is 7, therefore AC square is 7 square. Minus CB square. CB is 9, therefore CB square is 9 square. Minus AB square. AB is 6, therefore AB square is 6 square. Over 2 times AC, that is 7, times CB, that is 9. So in total, we actually found out that cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. So cosine theta equals to 7 squared. 7 squared is 49 plus 8 squared. 8 squared is 81 minus 6 squared, that is 36 over 2 times 7 times 9. 7 times 9 is 63, and 63 times 2 is 126. So in total we found out that cosine theta equals to 49 plus 81 is 130 minus 36 over 126. So cosine theta equals to 130 minus 36 is 94 over 126. So in total we should find out that cosine theta equals to 94 over 126. And 94 over 126 is equal to 0.7169. So cosine theta equals to 0.7169. You would like to find the value of angle theta itself, the size of angle theta. In order to find out the size of angle theta, we'll operate the opposite function of cosine, that is arc cosine, of the result of cosine theta, that is 0.7169. In this way, we get the value of angle theta itself. So, arc cosine of the result of cosine theta, that is 0.7169, it is equal to angle theta itself. The size is the size of angle theta. And if we arc cosine, can find out by using any simple scientific calculator that arc cosine of 0.769, it is equal to 40.368 degrees, and it is equal to theta. So if you found out that theta equals to 40.368 degrees in its size, what is the value of 180 degrees minus theta? 180 degrees minus theta, it is actually 180 degrees minus 40.368, it is actually equal to 139.632 degrees. And again, in total we should find out that 180 degrees minus theta equals to 139.362 degrees in its size. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent BC with this circle. This point is point L. We define the point of tendency of tangent AC with this circle. This point is point Q. And finally, we define the point of tendency of tangent AB with this circle. This point is point P. We will define the radius of this circle as R. And then we'll join points O and L together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle that equals to R according to our definition. So here we can implement rule 1, well, because the radius OL is equals to R, the radius OL is drawn to point L, that is the point of tendency of tangent BC with this circle. And here the radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by straight line. OQ is of course the radius of the circle that is equal to R. Point Q is the point of tendency of tangent CA with this circle, therefore according to rule 1, this angle equals to 90 degrees on its side, and this angle also equals to 90 degrees. We define the length of this line segment BL as A. So we can implement rule 2. Now triangle ABC. We have the circle. It has a couple of common external points, and therefore we can implement here rule 2. Application rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, this is the common external point, point P. For the common external point, point B, we have two tangents to this circle, tangent BL and tangent BP. And according to rule 2, they are equal to each other. It is to say, BL equals to BP. But BL is A according to our definition. Therefore, BP must be also equal to A since it's left according to rule 2. So they are equal to each other. AB equals to 6 units in its length, BP equals to A, and therefore AP equals to AB minus PB, that is 6 minus A. Likewise, this is the length of line segment LC. LC equals to BC, that is 9, minus BL, that is A. So total LP equals to 9 units in its length. In the next step, we will focus on this common external point, point A. From the common external point, point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP equals to 6 minus A, therefore AQ must be also equal to 6 minus A, according to rule 2, because they are equal to each other. In the next step, we'll focus on this common external point, point C. From common external point, this common external point, point C, we have two tangents to this circle, tangent CL and tangent CQ. And according to rule 2, they are equal to each other. That is to say, CL equals to CQ. But CL is 9 minus A, therefore CQ must be also equal to 9 minus A in its length according to rule 2. According to what is given in the question, side AC of triangle ABC equals to 7 units in itself. But AC side AC consists of two line segments, line segment AQ and line segment QC. And of course, therefore, side AC equals to the two line segments that it consists of. This is to say it is AQ plus QC. So AC equals to AQ plus QC. Plus QC. AC equals to AQ is 6 minus A plus QC. QC is 9 minus A. So in total we should find out that AC equals to 6 minus A plus 9 minus A. So AC equals to 6 plus 9 is 15. Minus A minus A. Minus A plus minus A is minus 2A. So in total AC equals to 15. 15 minus 2A. AC is 7, so AC by 7, so 7 equals to 15 minus 2A. Here we will add 2A to this equation, and we'll also subtract 7 simultaneously. We get that 2A equals to 15 minus 7 is 8, so 2A equals to 8. Here we divide this equation by 2, and finally get that A equals to 8 over 2, that is 4. So line 7 here is equals to A is equals to 4 units in there. Likewise, line 7 PB is also equals to A is equals to 4 units in there. Line 7 AP equals to 6 minus A, 6 minus A is 6 minus 4, that is 2. Likewise, AQ also equals to 6 minus A, that is 2. QC equals to 9 minus A. 9 minus A is 9 minus 4, that is 5. Likewise, LC equals to 9 minus A. This is line 7 LC equals to 9 minus A, that is 5. In the next step, we'll find out the semi-perimeter of this triangle, triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2. The perimeter of any triangle is equal to the sum of the side lengths of the triangle. In this case, it is AB plus BC plus AC. This is actually 6 plus 9 plus 7. S is the relation for the semi-perimeter. So the semi-perimeter of this triangle ABC equals to 6 plus 9 plus 7. That is the perimeter over 2. And again, if you found out that the semi-perimeter of this triangle ABC equals to the perimeter, that is 6 plus 9 plus 7 divided by 2. 6 plus 9 is 15, and 15 plus 7 is 22. So it is 22 over 2, that is 11. I should found out that the semi-perimeter of this triangle ABC equals to 11 units in its length. We define side AB of this triangle ABC is A. So AB equals to 6, AB equals to A equals to 6. We define side BC of this triangle ABC as B. So AC is equal to B equals to 9. And finally we define side AC of this triangle ABC as C. That is to say, side AC of this triangle ABC equals to C and C equals to 7. According to what is going to the question. So to that question found out that the semi-perimeter of triangle ABC equals to 11 units inside, A equals to 6, B equals to 7, and C equals to 9. Those are the depths of the sides of side depths of triangle ABC. Actually, we have a special formula for the area of any triangle. The special formula for the area of any triangle is as follows. Actually, the area of any triangle equals to, so the area of any triangle ABC could be any triangle. The area of triangle ABC, it is equals to the square root of S times S minus A times S minus B times S minus C. And again, the any triangle equals to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of the triangle. AB instead of the side depths of the triangle. So in our case, the area of our triangle ABC and the side depths of triangle ABC are as follows: A is 6, B is 9, and C is 7, and S, the semi-perimeter of triangle ABC, equals to 11 units in its length. The only thing that is left to do is to put the data, this data inside this equation, and find out the area of our triangle ABC. So we get that the area of triangle ABC will be equal to the square root of S. S is 11 times S minus A. S is 11, A is 6, so S minus A is 11 minus 6, that is 5, times S minus B. Again, S is 11, B is 9, so S minus B is 11 minus 9, that is 2, times S minus C. S is 11, C is 7, so S minus C is 11 minus 7, that is 4. So in total, we should find out that the area of triangle ABC is equal to the square root of 11 times 5 times 2 times 4. Here you will take 4 out of this root. The square root of 4 is 2, so the area of triangle ABC in total is equal to the square root of 2. Inside the root we left only with 11 times 5 times 2. So in total the area of triangle ABC equals to 2 times the square root of 11 times 5 times 2. The area of triangle ABC in total equals to 2 times inside the root we have 11 times 5 times 2. 11 times 5 is 55, and 55 times 2 is 110. So in total we should find out that the area of triangle ABC is equal to 2 times square root of 110 square root in size. The area of this triangle ABC equals to 2 times square root of 110 square root in size. Actually, we have a special formula for they have a triangle that is blocks a circle. And again, a special formula for the area of any triangle that blocks a circle. This is a triangle ABC that blocks the circle. So we use the special formula in order to find out the area of triangle ABC, this triangle that blocks this circle. According to the special formula, the area of any triangle that blocks a circle is equal to S times R. S is the semi-perimeter of the triangle that blocks the circle, and R is the circle that is described by the triangle. So again, S is the semi-perimeter of the triangle, and R is the radius of the circle that is described by the triangle. We already found out that the triangle ABC equals to 2 times square root of 110 square roots in size, and is equals to S. S is 11 times R. The radius of this circle R that is described by triangle ABC is the missing variable, so we leave it as it is. So in total, we found out that 2 times square root of 110 equals to 11 times R. And again, 2 times square root of 110 equals to 11 times R. Here we divide this equation by 11 and get that the radius of this circle R that is described by triangle ABC is equal to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is equal to 1.907 units in its length. So in total, we actually found out that the radius R of this circle that is described by triangle ABC is equal to 1.907 units in its length. What is a sector? It's a sector OQL. What is a sector? Sector OQL is a portion of this circle that is enclosed by 2 radii and RQL between those 2 radii. And again, the green shape AOB is a sector. Sector AOB is a portion of this circle that is enclosed by those 2 radii and RKB between those 2 radii. The 2 radii are defined as the legs of the sector. Angle theta is the angle that is located between those 2 legs of the sector AOB. So what is the area of this sector AOB? The area of any sector equals to pi r squared, that is the area of this circle that contains this sector, times the angle between the legs of the sector that is theta over 360 degrees. Repeat again, the area of sector AOB. Here the rounded line above AOB is the sign for a sector. So the area of sector AOB equals to pi r squared times theta over 360 degrees. Okay. So this is sector QOL. Our task is to find out the area of this green shape. So what is the area of this green shape? from the drawing it is very easy to see that the area of this ring shape equals to the area of quadrilateral QOLC minus the area of this sector QOL. Okay, again, the area of this ring shape in total equals to the area of this quadrilateral QOLC minus the area of this sector QOL. So write it down. The area of the green shape, this green shape in total is equals to the area of the big quadrilateral QOLC minus the area of the sector QOL. Before we continue, we'll focus on quadrilateral QOLC. You know that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so again, the sum of the angles in any quadrilateral is equal to 360 degrees. So which angles we have inside this quadrilateral QOLC? $90 degrees plus 90 degrees is 180 degrees plus theta plus the missing angle QOL must be equal to 360 degrees according to the rule that I mentioned. So 180 degrees plus theta plus this missing angle that is angle QOL in total, the sum of those four angles must be equal to 360 degrees according to the rule that I mentioned. Okay, again, we should find out that 180 degrees plus theta plus the missing angle QOL total must be equal to 360 degrees. Here we subtract 180 degrees from this equation. And you get that here 180 degrees get cancelled. So we left only with theta plus the missing QOL total is equal to 360 degrees minus 180 degrees, it is 180 degrees. So theta plus the missing QOL equals to 180 degrees. Here we subtract theta from the equation. And how you get that the missing angle QOL is equal to 180 degrees minus theta. And again, the missing angle QL equals to 180 degrees minus theta. But we already found out that $180 degrees minus theta equals to 139.632 degrees. This is the missing angle QOL, is equal to 180 degrees minus theta, and 180 degrees minus theta equals to 139.632 degrees. And again, the missing angle QOL equals to 139.632 degrees. Okay, again, our task is to find out the area of this green shape. So the area of this green shape equals to the area of quadrilateral QOLC minus the area of this sector POL. So if you don't, if you found out that the area of this green shape equals to the area of this quadrilateral QOLC. Now there of this sector QOL. So if it again, I should found out that there of the green shape in total equals to there of quadrilateral QOLC minus there of sector QOL. In the next step, we'll join points O and C together by a straight line. By joining points O and C, we divided quadrilateral QOLC into two parts. Those are the two parts. The first part, it is actually the right triangle OQC, and the second part is this right triangle OLC. So the area of sector, the area of quadrilateral QOLC must be equal to the sum of the areas of the two shapes that it consists of. It consists of those two shapes. So the area of quadrilateral QOLC must be equal to the area of the first shape, that is the right triangle QOC, plus the area of the second shape, that is the second shape that it consists of, that is the area of this triangle OLC. So write it down. We should remember that the area of this quadrilateral QOLC equals to the area of this right triangle OQC plus the area of the second shape that it consists of, this actually the area of this right triangle OLC. And again, we should find out that the area of this quadrilateral QOLC equal to the area of the first shape that it consists of, that is actually the right triangle, the area of the right triangle OQC plus the area of the second shape that it consists of, that is actually the area of the right triangle OLC. So we have to subtract the area of sector QOL. What is the area of this sector QOL? According to the formula that I presented to you a couple of minutes ago, the area of the sector QOL must be equal to the area of the circle that contains the sector, that is pi r squared, and r is the radius of the circle. So it is pi r squared times the angle between the legs of the circle, that is 139.632 degrees, over 360 degrees. So in total, we should find out that the area of sector QOL is equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the sector, between the legs of the sector, that is 139.632 degrees, over 360 degrees. What is the area of this right triangle QOC? The area of any triangle equals to the base of the triangle times the height over 2. The base is QO, that is R. The height is QC, that is 5, divided by 2. So in total, the area of this right triangle QOC equals to 5R over 2. So if you found out that the area of the right triangle QOC equals to 5R over 2, square units in its size, plus the area of the second right triangle, the right triangle OLC. The area of this right triangle OLC equals to the base OL, that is R, that is the radius of the circle, times the height LC, that is 5 over 2. So in total, they have this right triangle OLC equals to 5R over 2. Again, they have the right triangle OLC equals to 5R over 2. Minus the area of this sector, or QOL, equals to pi r squared times 139.632 degrees over 360 degrees. R equals to 1.907. We found out that the radius of this circle R equals to 1.907. So we substitute R by 1.907. So therefore R squared must be equal to 1.907 squared. So in total, the sector POL equals to pi times 1.907 squared times 139.632 degrees over 360 degrees. So in total, the area of sector POL, the area of sector QOL, the sector QOL is equal to pi times 1.907 squared times 139.632 degrees or 360 degrees. So they have the green shape in total. Is equal to 5R over 2 plus 5R over 2. Minus the area of the sector, this expression. Showing the value of this expression, pi times 1.907 squared times 139.632 degrees over 360 degrees. In total, the area of this expression is equal to 4.387 square meters in size. 4.387 square meters in size. So in total, the area of sector QOL is equal to 4.387 square meters in size. So the area of the green shape equals to 5R over 2 plus 5R over 2 is 5R minus 4.387. R is 1.907, therefore 5R is 5 times 1.907, therefore equal to 9.535 minus 4.387. 9.535 minus 4.387. In total, it is equal to 5.148 square meters in its size. So if you found out that they have this green shape, that is the area that you are looking for this question, is equal to 5.148 square meters in its size. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question by using 3 different methods. our task in the second question is to find out the area of this curve, square ABCD. So in the drawing, we have square ABCD. This is diagonal DB of square ABCD. This is angle PDP. This is equals to 30 degrees in size. This is angle PBC. This is also equals to 30 degrees in size. This is line 7 PB. This is equals to 5 units in its length. Again, our task is to find out the area of this curve, square ABCD. So we'll start with the first method. So we know that the diagonals of any square bisect the angles of the square. Again, the diagonals of any square bisect the angles of the square. Diagonal DB of square ABCD bisect angle ABC. This is the first half, this is 45 degrees. This is the second half. It is also equals to 45 degrees in size. But this angle equals to 40 degrees, therefore this angle must be equal to 15 degrees in size. Likewise, diagonal BD bisect angle ADC. This is the first half of angle ADC, that equals to 45 degrees in its size. This is the second half of angle ADC, that is also equal to 45 degrees in size. So this angle equals to 30 degrees, and therefore this angle must be equal to 15 degrees in its size. So in triangle BDP, we have 15 degrees plus 30 degrees. This angle equals to 15 degrees in size, this angle equals to 30 degrees in size. 15 plus 30 is 45, and therefore this angle must be equal to 135 degrees in size. In the next step, we do a construction, that is to say from point C, we draw an angle bisector of angle BCD. So this is an angle bisector, therefore this angle equals to 45 degrees, and this angle also equals to 45 degrees. In the next step, we extend line 7DP until it touches the angle bisector. And we define the touching point of the extended line 7DP with this angle bisector. This point is point Q. when doing this construction, we created triangle DQC. The triangle DQC, this angle equals to 15 degrees, this angle equals to 45 degrees. 15 plus 45 is 60. Therefore, this missing angle must be equal to 120 degrees in its size. According to the rule that the sum of the angles in an triangle is equal to 180 degrees. In the next step, we join points P and Q together by a straight line. By joining points B and Q, create triangle BQC. In the next step, we'll prove that those two triangles can go into each other according to side angle side rule. That is to say, we'll prove that triangle BQC can go into this triangle CQD according to side angle side rule. So I don't know, we have to find out, we have to prove that triangle BQC can go into this triangle DQC according to side angle side rule. So why those two triangles can go into each other? First of all, side BC of triangle BQC equals to side DC of triangle DQC. They are both the sides of a square, therefore they are equal to each other. So BC equals to DC. BC equals to DC. And again, if you remember that side BC of triangle QBC equals to side DC of triangle DQC, they are both the sides of a square, therefore they are equal to each other. In addition, those two angles they are both equal to 45 degrees, and therefore they are equal to each other. So here this is angle BCQ. In triangle BQC, this is equal to this angle. This is actually angle DCQ and triangle DQC. Okay, again, I should found out that angle BCQ and triangle BQC equals to angle DCQ and triangle DQC. They are both equal to 45 degrees, and therefore they are equal to each other. And finally, QC is a constant that belongs to both triangles. QC definitely belongs to triangle QCB, and QC definitely belongs to triangle QCD. So QC is a common side that belongs to both triangles. But again, QC equals to itself, it's a common side that belongs to both triangles. So we actually found out that those two sides and the angle that is included between those two sides in this triangle BQC are corresponding equal to those two sides, and the angle that is included between those two sides in this triangle DQC. Therefore, those two triangles can go into each other according to side angle side rule. Here, those two sides and the angle that is included between those two sides in triangle BQC are corresponding equal to those two sides, and the angle that is included between those two sides in triangle DQC. Therefore, those two triangles can go into each other according to side angle side rule. So triangle BQC equals the congruent to triangle DQC according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that those two corresponding angles must be also equal to each other and their sizes. So I get this is again QDC and it equals to this angle, the other angle QBC. Those triangles are equal to each other according to the rule that corresponding angles can combine triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other and their sizes. So if we found out that angle QDC equals to angle QBC. But we already found out that angle QDC equals to 15 degrees in side, so I can argue that angle QDC equals to 15 degrees, and for this equation 15 degrees equals to angle QDC equals to angle QBC, we derive that those two sides are equal to each other, so angle QBC equals to 15 degrees in its sides. So here, this is angle QBC that is equals to 15 degrees in its size. We know that diagonal DB bisect angle ABC. The first half is 45 degrees. This is the second half. It also equals to 45 degrees in its size. So we have 15 degrees plus 15 degrees is 30 degrees. Therefore, this angle must be equal to 15 degrees in size because 15 times 4 is 45. That is the size of the second half. So this angle equals to 15 degrees in its size. So in triangle DQB, this is triangle DQB, this angle equals to 30 degrees plus 15 is 30. This angle also equals to 30, so 30 degrees plus 30 degrees is 60 degrees, and therefore this angle must be equal to 120 degrees in size. According to the rule that the sum of the angles in any diagonal is equal to 180 degrees. Likewise, this triangle BQC, this angle equals to 15 degrees, this angle equals to 45 degrees, 15 degrees plus 45 degrees is 60 degrees, and therefore this third piece angle must be equal to 180 degrees in size according to the same rule. So, in the next step, we'll prove that those two triangles can go into each other. But before that, we focus on this triangle DBP. So I copy this triangle DBP in a new page and analyze this triangle DBP. Actually, what is the size of this angle? What is the size of angle BPQ? The size of this angle BPQ. We have the rule that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So the sum of the angles on the right side of the straight line DQ at point P must be equal to 180 degrees. Which angles we have on this right side of the straight line DQ at point P? We have 135 degrees plus the missing angle. In total must be equal to 180 degrees according to rule 2. According to rule 3, that said that the sum of the angles on one side of a straight line is equal to 180 degrees. So 135 degrees plus the missing angle in total must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 45 degrees in size. Because 135 degrees plus 45 degrees, it is 180 degrees. That is the sum of the angles on the right side of the straight line DQ at point P according to rule 3. Therefore, this missing angle must be equal to 45 degrees in size. In the next step, we'll prove that triangle BPQ can run to this triangle BQC. Repeat again, we'll prove that those two triangles can run to each other according to angle side angle rule. So to prove that triangle BQC can run to this triangle PQB according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 45 degrees and therefore they are equal to each other. So actually this is angle Q, this is angle QCB in the right triangle QBC. This is equal to this angle, this is angle BPQ. In triangle QBP. Okay, then we found out that angle QCB, triangle BQC equals to angle BPQ, and triangle PQB. They are both equal to 45 degrees and therefore they are equal to each other. In addition, this is side QB, this is a common side that belongs to both sides. Side QB is definitely belongs to triangle BQC, side QB definitely belongs to triangle BQP. So QB is a common side that belongs to both triangles. side QB equals to itself is a common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees and therefore they are equal to each other. So actually this is angle QBC and triangle PQC. And it is equal to this angle, this is actually angle PBQ and triangle PQB. But again, I should follow that angle PBC triangle PQB is equal to angle PBQ triangle PQB, again angle PBC triangle PQC equals to angle PBQ triangle PQB. They are both equal to 15 degrees and therefore they are equal to each other. So if you found out that those two angles and the side that is included between those two angles in this triangle PQB are correspondingly equal to those two angles and the side that is included between those two angles, that is side QB, in this triangle QBC. And therefore those two triangles can go to each other according to angle side angle rule. We have those two angles and the angle and the side that is included between those two angles in this triangle QBC are correspondingly equal to those two angles and the side that is included between those two angles in this triangle QBP. And therefore those two triangles can go into each other according to angle side angle rule. So it's another found out that angle triangle BQC congruent, this is the sign of congruent, to triangle PBQ according to angle side angle rule. And from the fact that those two triangles can go into each other, we realize that side PB is equal to the corresponding side BC. Why side PB is the corresponding side of side BC? Because in triangle PQB, side PB is located in front of this angle that is 120 degrees in its size. Likewise, in this triangle PQC, side BC is located in front of this angle that is also equal to 120 degrees in its size. So those two sides are corresponding sides. So according to the rule that corresponding sides and congruent triangles are equal to each other, we get that those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in real lengths. So if you found out that BP equals to BC, or PB equals to BC. Again, if you found out that PB equals to BC. But according to what is given in the question, PB equals to 5 units inside. So we write down that PB equals to 5. And from this equation, 5 equals to PB equals to BC, we derive that BC also equals to 5. But those two sides of the equation are equal to each other. So BC equals to 5. And I hear that BC equals to 5. And the test is to find out they have this square ABCD. So what is the square ABCD? Actually, we know that the area of any square equals to the length of one side squared. Therefore, the area of square ABCD must be equal to the length of one side, that is BC squared. But BC is 5. Therefore BC squared is 5 squared. 5 squared is 25. So in total, we found out that there are for square ABCD is equal to 25 square units in size. And again, we found out that the area of the square ABCD is equal to 25 square units in size. So we finish with the first method. In the next step, I will present to you how to find out the area of the square ABCD according to the second method. Diagonal DB bisect angle ABC. This is the first half. This is equal to 45 degrees in size. This is the second half of angle ABC. That is also equal to 45 degrees in size. But this angle equals to 30 degrees, and therefore the missing angle must be equal to 15 degrees in size. Okay. Likewise, diagonal BD bisect angle ADC. This is the first half of angle ADC. This is equal to 45 degrees inside. This is the second half of angle ADC. That is also equal to 45 degrees in size. So 30 degrees plus the missing angle is 45 degrees. So the missing angle must be equal to 15 degrees in size. So in triangle BDP, 30 degrees plus 15 degrees is 135 degrees, and therefore this third missing angle must be equal to 135 degrees in size according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we will do a construction. That is to say, we will draw a circle around square ABCD in such a way that point A will be the center of the circle that we will draw, and AB will be the radius of the circle. So AB is the radius of the circle, AD is also the radius. We will define the radius AB is x, the radius AD is also x. Repeat again, the center of the circle that will go around square ABCD will be at point A, and the radius of the circle is the sine length of square ABCD that is defined as x. Okay, this is the circle that we draw around square ABCD. So as I mentioned before, point A is the center of the circle, and the radius of this circle equals to AB, that is the sine length of square ABCD. AD is also the radius, that is x. So AB is the radius of the circle. The radius of a circle has two edges. The first edge of any radius of any circle must lie on the center of the circle, that is point A. The second edge of any radius of any circle must lie on the circle itself, because it is a radius. This is the definition of a radius. Therefore, point B is located on the circle itself. because AB is the radius. That is to say, the circle passes from point B. Likewise, AD is also the radius of the circle. The first edge of radius AD lies on point A, that is the center of the circle. It is true for any triangle, for any radius. Therefore, it must be true for the radius AD. The first edge of radius AD must lie on the center of the circle, while the second edge of the radius AD must lie on the circle itself, because it is a radius. So point D lies on the circle itself. So we can find out in total, in conclusion, that points B and D, the circle passes from points B and D. So the B and D are there on the circle. Okay. In the next step, we'll join points A and P together by a straight line. This is angle DPB. This is equals to 135 degrees in its size. This is angle DBP. This is equals to 135 degrees in its size. We know that the sum of the angles around any point is equal to 360 degrees. Again, the sum of the angles around any point is equal to 360 degrees. And therefore, the sum of the angles around point A must be equal to 360 degrees. Which angles we have around point A? We have this is a right angle plus the missing angle. In total must be equal to 360 degrees. Therefore, this missing angle must be equal to 270 degrees in its size. The big angle DAB equals to 270 degrees in its size. But the big angle DAB is the central angle, because the vertex is located on the center of the circle. So central angle DAB equals to 270 degrees in its size. This is angle DBP. This equals to 125 degrees in its size. So angle DBP is equal to half of angle DAB. 270 degrees over 2 is 125 degrees. So central angle DAB is twice as large of angle DBP. Okay. So here we can implement all 18. Because of the fact that central angle DAB is twice as large of angle DBP, can implement all 13. According to all 13, the size of central angle DAB subtend on chord DB. Angle DBP also subtend on the same chord DB. And according to all 13, the size of central angle DAB must be twice as large as the size of a peripheral angle that subtend on the same chord. Central angle DAB equals to 220 degrees, subtend on chord DB. Likewise, angle DBP also subtend on chord DB. So those both angles subtend on the same chord DB. And according to all 13, the size of the central angle DAB must be twice as large as the size of peripheral angle DBP that is subtend on the same chord DB. They are both subtend on the same chord DB. So peripheral angle DBP is twice as large, is half of the size of central angle DAB, because 270 degrees over 2 is 125 degrees. So we can find out that peripheral angle DBP obeys to all 15, because it is half of the central angle, and they are both located on the same chord DB. From the fact that angle DBP obeys to all 15, we must conclude that angle DBP is a peripheral angle. So please check on all 13. According to all 13, the central angle is twice as large as the peripheral angle subtended on the same chord. In the drawing, we have a circle. This is peripheral angle ACB. This is equals to 30 degrees in size. This is central angle AOB. This is equals to 2. This is central angle AOB that subtend on the same chord AB like peripheral angle ACB. So those two angles are both subtend on the same chord AB. And therefore, the size of this center in AOB must be twice as large as the size of this peripheral in CB. The size of this peripheral in CB is theta, and therefore the size of this center in AOB must be equal to 2 theta. Here we have the size of peripheral center in BAD, the subtend of chord DB is 270 degrees. The size of this second DBP that subtend on the same chord DB, equals to 135 degrees. So the size of the center DAB is twice as large as the size of angle DBP. And they are both subtend on the same chord DB. So angle DBP is obeys to Rule 13 because according to Rule 13, the size of the center angle is twice as large of the size of the peripheral angle that subtend on the same chord. They are both subtend on chord BD, and the size of center angle DAB is twice as large as the size of this peripheral angle DBP. And therefore, angle DBP must be a peripheral angle because it obeys to Rule 13. And because of the fact that DBP is a peripheral angle, all of its three vertices, DP and B, must locate on the circle itself, because any peripheral angle, all of its three vertices must be located on the circle itself. Point D is located on the circle, point B is located on the circle, and point P must be also located on the circle itself. So, in conclusion, I found out that this circle passes for point P, because point P is located on the circle. Point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, this is equal to X. So here we have angle PBA. This is angle PBA. This is equals to 45 degrees plus 15 degrees is 60 degrees. So in triangle ABP, angle ABP equals to 60 degrees. In the next step, we'll copy triangle ABP in a new page and we analyze this triangle ABP. So I'll copy triangle ABP in a new page and we analyze this triangle ABP. Repeat again, angle ABP equals to 60 degrees in size. 45 degrees plus 15 degrees is 60 degrees. Actually, this is triangle ABP, this is a comment from the original drawing. Angle ABP equals to 60 degrees in size. We have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But this angle equals to 60 degrees in size, therefore this missing angle must be also equal to 60 degrees in size according to the rule that I mentioned. So in triangle ABP, 60 degrees plus 60 degrees is 120 degrees, and for this missing must be equal to 60 degrees inside according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in triangle ABP we have all the flares are equal to 60 degrees in their sizes, therefore triangle ABP is an equilateral triangle. You know that all the sides of an equilateral triangle are equal to each other. So in equilateral triangle ABP, side PB is equal to side AB. But according to all this given the question, PB equals to 5. So we can write here that PB equals to 5. And from this equation, 5 equals to PB equals to AB, we know that AB equals to 5. Those two sides of the equation are equal to each other. So AB equals to 5. This is side AB of square ABCD is equals to 5 units in its length. Note that our task is to find out the area of this square ABCD. So what is the area of square ABCD? You know that the area of any square equals to the length of one side squared. So the area of square ABCD must be equal to the length of AB squared. The length of AB squared. AB is 5. Therefore AB squared is 5 squared. 5 squared is 25. So the area of square ABCD is equal to 35 squares in its size. According to the second method, so if we arrive to the same result as the first method, so finish with the second method. In the next step I present you how to find out the area of this square ABCD according to the second method, or according to the first method. Diagonal DB bisect angle ABC. This is the first half of angle DC, this is 45 degrees. This is the second half of angle ABC. This is also equals to 45 degrees in its size. 30 degrees plus the missing angle must be equal to 45 degrees. Therefore, the missing angle must be equal to 15 degrees in its size. So in triangle DBP, 30 degrees plus 15 degrees is 45 degrees, and therefore this third missing angle must be equal to 135 degrees in its size. According to the rule, it's said that the sum of the angles in any triangle is equal to 180 degrees. We define side AB is x, side AD must be also equal to x because it is a square. This is a right angle because ABCD is a square. In the next step, we will implement the Pythagoras theorem on this right angle ADB. The right angle ADB, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right angle ADB, DB squared, that is the square of the hypotenuse, is equal to AD square plus AB square. dB is the missing side, so it is this, so it is dB square equals to AD square. AD is x, therefore AD square is x square plus AB square. AB is also x, so AB square is x square. But if you want to know that dB square equals to x square plus x square, that is 2x square. dB square equals to 2x square. Here we take out all of this equation and find that dB equals to the square root of 2 times the square root of x squared. The square root of x squared is x. So in total, we should find out that the length of the hypotenuse dB is equal to square root of 2 times x units in its length. In the next step, we will implement the law of sines. This triangle by BDP. The law of sines is true in any triangle, therefore we can implement the law of sines in this triangle DBP. So what is the law of sines? This is a triangle ABC that would be any triangle. This is side AB of triangle ABC that is equals to C units in its length. This is side AC that is equals to B units in its length. This is side BC that is equal to A units in its length. This is angle BAC that is equal to capital A degrees in its size. This is angle ABC that is equal to capital B degrees in its size. This is angle ACB that is equal to capital C degrees in its size. So this triangle ABC that could be any triangle. According to the law of sines, the following equation is true. That A over sinus A equals to B over sinus B equals to C over sinus C. Again, it's triangle ABC, A over sinus A equals to B over sinus B equals to C over sinus C. So we can implement the law of sines in this triangle by DBP. According to the law of sines, in triangle DBP, the following equation is true. That dB over sinus 135 degrees is equal to BP over sinus 30 degrees. Again, this triangle DBP, according to the law of sines, the following equation is true. The dB over sinus 135 degrees equals to BP over sinus 30 degrees. We already found out that dB equals to the square root of 2 times x over sinus 135 degrees. Sinus 135 degrees is equals to the square root of 2 over 2. And it equals to BP. BP is 5 according to what is given as a question. Over sinus 30 degrees. Sinus 30 degrees is 1 half. So in total, if you want to know that square root of 2 times x over square root of 2 over 2 equals to 5 over 1 half. Here we'll move 2 to the denominator and square root of 2 to the denominator and get that in total the value of this expression equals to the square root of 2 times x times 2 over square root of 2 and is equal to 5 over 1 half. 5 over 1 half is 10. So in total, we found out that square root of 2 times x times 2 over square root of 2 equals to 10. Here we have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. And in this side of the equation, we left only with 2x equals to 10. Here we divide this equation by 2 and we get that x equals to 10 over 2 is 5. X is the sine of square ABCD. The test is to find out the area of this square ABCD. Actually, we know that the area of any square equals to the area of one side squared. The area of one side is x, therefore the area of one side squared is x squared. The area of square ABCD equals to x squared. X is 5, therefore x squared is 5 squared, that is 25. 25 square units. So, in all the three methods, we should find out that the area of the square ABCD is equal to 25 square units in its size. So in the next step, I will summarize the lecture. We start with the first question, of course. Our task in the first question was to find out the area of this grand shape. So, in the drawing, we have a circle that is described by this triangle ABC. We know that side AB is equals to 6 units in itself, side AC of triangle ABC equals to 7 units in itself. And side BC of triangle ABC equals to 9 units in its length. Repeat again that our task is to find out the area of this grand shape. So first of all, we defined angle ACB, this angle is theta. And we implemented the law of cosines in this triangle ABC. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to 1 unit in itself, side AC equals to 2 units in itself, side BC equals to 3 units in its length. This angle BAC is equals to theta degrees in its size. So in this triangle BAC, according to the law of cosines, the following equation is true. That cosine theta equals to a squared plus b squared minus c squared over 2 times a times b. Again, cosine theta equals to a squared plus b squared minus c squared over 2 times a times b. Again, if we implement the law of cosines, this triangle ABC, according to the law of cosines, we get that cosine theta equals to ac squared plus cb squared minus ab squared over 2 times ac times cb. Okay, again, according to the law of cosines, this triangle ABC, the following equation is true. That cosine theta equals to ac squared plus bc squared minus ab squared over 2 times ac times cb. This equation is the implementation of the law of cosines in our triangle ABC. So cosine theta equals to AC square. AC is 7, therefore AC square is 7 square. Plus CB square. CB is 9, therefore CB square is 9 square. Minus AB square. AB is 6, therefore AB square is 6 square. Over 2 times AC, that is 7, times CB, that is 9. So in total, if you found out that cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. 7 square is 49, plus 9 square is 81, minus 6 square, that is 36. Over 7 times 9 is 63, 63 times 2 is 126. So cosine theta equals to 49 plus 81 is 130, minus 36 over 126. So in total, if you found out that cosine theta equals to 130 minus 36 over 126. So cosine theta equals to 130 minus 36 is 94 over 126. 94 over 126 equals to 0.7169. In total, if you found out that cosine theta equals to 0.7169. We would like to find out the value of theta itself. In order to find out the value of angle theta, we'll operate the opposite function of cosine, that is arc cosine, on the result of cosine theta, that is 0.7169. In this way, we get the value of angle theta itself. So arc cosine of the result of cosine theta, this is 0.7169, is equal to the size of angle theta. You can find out in any simple calculator, scientific calculator, that other cosine of 0.7169 equals to 40.368 degrees. So total, if you found out that angle theta equals to 40.368 degrees in its size. Therefore, 180 degrees minus theta equals to 180 degrees minus 40.368. This actually equals to 139.632 degrees. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent BC with this circle. This point is point L. Likewise, we define the point of tendency of tangent AB with this circle. This point is point P. And finally, we define the point of tendency of tangent AC with this circle. This point is point Q. We define the radius of the circle as R. We join points O and L together by side line. Point O is the center of the circle. Point L is the point of the circle itself. Therefore, OL is the radius of the circle that equals to R according to our definition. The radius of OL that is equals to R. The radius of OL is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by side line. Point Q is the point of tendency of tangent AC with this circle. Therefore, so OQ is of course the radius of this circle. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So, in the next step, we defined the length of line segment BL as A, and we implemented rule 2 in our drawing. I'll repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint, point P. From the common standpoint, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. Why? Because this is point B, this is the common standpoint of this circle. Why point B is the common standpoint? Because it is located outside the circle, and on point B we have two tangents to the circle, tangent BL and tangent BP. And according to rule 2, they are equal to each other. That is to say, BL equals to BP, but BL is A, therefore BP must be also equal to units itself according to rule 2. So BP equals to A, AB equals to 6. So PA equals to AB, that is 6, plus BP is A. So total PA equals to 6 minus A. Likewise, side BC equals to 9 units in itself, side A equals to 8 units in itself, and therefore LC equals to AC, that is 9, minus AL, that is 8. So in total, LP AC equals to 9 minus 8 units in itself. So the next step, we focus on this common sum point A. From the common sum point A, we have two tangents to the second, tangent AP and tangent AQ. The from the two, they are equal to each other. That is to say, AP equals to AQ. But AP is 6 minus 2A. Therefore, AQ must be also equal to 6 minus 8. Therefore, AQ must be also equal to 6 minus 7 in itself, according to all two. Likewise, focus on this common sum point C. From the common sum point C, we have two tangents to the second, tangent CL and tangent CQ. And according to all two, they are equal to each other. That is to say, CL equals to CQ, but CL is 9 minus 8, therefore CQ must be also equal to 9 minus 7 in itself. It's given us the equation that side AC of triangle ABC equals to 7 units in itself. Side AC consists of two line segments, AQ and QC. Therefore, AC must be equal to the two line segments that it consists of. That is to say, it must be equal to AQ plus QC. AQ is 6 minus 8 plus QC, that is 9 minus 8. So in total, AC equals to 6 minus 8 plus 9 minus 8. So AC equals to 6 plus 9, that is 15, minus 8 minus 8 minus 2A. So in total, AC equals to 15 minus 2A. AC is 7, so we subtract AC by 7. So 7 equals to 15 minus 2A. Here we subtracted, we added 2A to the equation, and we subtracted 7 simultaneously, and found out that actually that 2A equals to 15 minus 7, that is 8. So 2A equals to 8. Here we divided this equation by 2, and found out that A equals to 8 over 2, that is 4. This is line 7BM, that is equals to 8, that is equals to 4. This is line 7BP, that is equals to 8, and A equals to 4. This is line 7AP, that is equals to 6 minus 8. 6 minus 8, 6 minus 4, that is 2. Likewise, AQ equals to 6 minus 8, that is 2. QC equals to 9 minus 8. 9 minus 8 is 9 minus 4, that is 5. And finally, LC equals to 9 minus 8, that is 5. So, in the next step, found out the semi-perimeter of this triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2. The perimeter of any triangle is equal to the sum of the lengths of its three sides. In this case, it is AB, this is equal to 6 plus BC, this is 9, plus AC, that is 7. So in total, the perimeter is equal to 6 plus 9 plus 7. And therefore, the simple perimeter is equal to the perimeter over 2. So the simple S is the abbreviation for the semi-perimeter. S is the semi-perimeter. Is equal to 6 plus 9 plus 7 over 2. 6 plus 9 is 15, 15 plus 7 is 22, over 2 is 11. So in total, we found out that the semi-perimeter of this triangle ABC equals to 11 units in itself. Side AB is defined as A, that is 6. Side BC is defined as side AB is defined as A, that is 6. Side BC, it is defined as B, that is 9. This is side AC, that is defined as C, that is 7. So in total, A equals to 6, B equals to 9, and C equals to 7. We have a special formula to find out the area of any triangle. The area of this triangle ABC according to the special formula is equals to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of this triangle, that is 11. A, B, and C are the side lengths of this triangle ABC. A equals to 6, B equals to 9, C equals to 7. So in this triangle ABC, the area of triangle ABC equals to the square root of S is 11 times S minus A. S is 11, A is 6, so S minus A is 11 minus 6, that is 5, times S minus B. S is 11, B is 9, so S minus B is 11 minus 9, that is 2, times S minus C. S is 11, C is 7, so S minus C is 11 minus 7, that is 4. So in total, we should find out that the area of triangle ABC, it is equals to the square root of 11 times 5 times 2 times 4. The square root of 4 is 2. So we took 4 out of this root. We should find out that the area of triangle ABC equals to 2. This is the square root of 4. Inside the root we left only if 11 times 5 times 2. 11 times 5 is 55. 55 times 2 is 110. So in total inside the root we left only with 110 times 2. So in total we found out that the area of triangle ABC equals to 2 times root of 110. We have a special formula for the area of any triangle that blocks a circle. Triangle ABC blocks this circle, so we can use the new formula in order to find out the area of triangle ABC that blocks this circle. Actually, according to the new formula, the area of triangle ABC equals to the semi-perimeter S times R is the radius of the circle that is blocked by triangle ABC, or R is the radius of this circle that is inscribed by triangle ABC. And again, the area of triangle ABC according to the new formula equals to the semi-perimeter S times the radius R that is inscribed by triangle ABC. So we already found out that the triangle ABC equals to 2 times root of 10, square unit in size. S is 11, R is the missing radius of the circle that is described by triangle ABC. So in total, we found out that 2 times root of 110 equals to 11 times R. Here we divided this equation by 11 and finally found out that R, the radius of this circle that is described by triangle ABC, equals to 2 times root of 110 over 11. 2 times root of 211 is 1.907. So in total, we found out that the radius of this circle that is described by triangle ABC, it is equal to 1.907 units in its length. This is quadrangle QOLC. We have the rule that said that the sum of the areas in any quadrangle is equal to 360 degrees. And therefore the sum of the areas in quadrangle QOLC equals to 360 degrees. Which angles we have in quadrangle QOLC? We have 90 degrees plus 90 degrees, it is 180 degrees, plus angle theta plus the missing angle, in total must be equal to 360 degrees according to the rule that I mentioned. So if we found out that the sum of the angles in quadrangle QOLC equals to 180 degrees plus theta plus the missing angle QOL, in total must be equal to 360 degrees. We subtracted 180 degrees from this equation, so 180 degrees will get cancelled. We left only with theta plus the missing angle QOL in this side of the equation. In the other side of the equation, we have 360 degrees plus 180 degrees, it is 180 degrees. So in total, we should find out that theta plus the missing angle QL equals to 180 degrees. Here we subtract the theta from this equation and finally found out that the missing angle QL equals to 180 degrees minus theta. This is the missing angle QL that equals to 180 degrees minus theta. With its size. But we already found out that 180 degrees minus theta equals to 139.632 degrees. We can write here that the missing angle QL is equal to 180 degrees minus theta is equal to 139.632 degrees in its size. In the next step, we defined the notion of a sector. What is a sector? This is sector QOL. A sector is a portion of a circle. We can say that sector QOL is a portion of this circle enclosed by two radii and RQL between them. RQL between them. Okay, again, actually, the green shape AOB is a sector. It is a portion of this circle enclosed by those two radii and RKB between those two radii. The two radii are defined as the length of the sector. This is the angle theta that is located between the lengths of the sector. What is the area of this green sector AOB? The area of the sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the sector, that is theta, over 360 degrees. And repeat again, the area of sector AOB equals to pi r squared times theta over 360 degrees. Our task is to find out the area of this green shape. What is the area of this green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of quadrilateral QOLC minus the area of this sector QOL. Repeat again, the area of this green shape equals to the area of this quadrilateral QOLC minus the area of this sector QOL. Very simple. Repeat again, we shall know that the area that we are looking for in this question, that is the area of the green shape equals to the area of quadrilateral QOLC minus the area of sector QOL. The rounded line above QL is the sign for the sector. It means sector QOL. In the next step, we join points O and C together by straight line. By joining points O and C, we divided quadrilateral QOLC in two parts. Those are the two parts. The first part is square OQC, and the second part is square OLC. It is very clear that the area of sector QOL is equal to the sum of the areas of the two shapes that it consists of. Quadrilateral QOLC consists of two shapes, and therefore the area of quadrilateral QOLC must be equal to the area of the first shape, that is actually the area of this right triangle QOC, plus the area of the second shape that it consists of, that is actually the area of this right triangle OLC. Which is found out in total the area of quadrilateral QOLC equals to the area of the first shape that it consists of, that is actually the area of the right triangle QOC, plus the area of the second shape that it consists of, that is actually the area of the right triangle OLC, minus the area of this sector QOL. We already found out, I already explained to you that the area of any sector equals to pi r squared, that is the area of this circle that contains the sector, r is the radius of the circle, times the angle between the legs of the circle, that is 139.632 degrees over 360 degrees. Repeat again, the area of this sector QOL in total is equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle, that is 139.632 degrees over 360 degrees. What is the area of this right triangle QOC? The area of any triangle equals to the base of the triangle times the height over 2. We choose the base as QO, that is R, times the height QC, that is 5 over 2. So in total, the area of this triangle QOC equals to 5R over 2. Again, the area of triangle QOC equals to 5R over 2. Plus the area of this right triangle OLC. The area of this right triangle equals to the base OL, that is R, times the height LC, that is 5. So in total, divided by 2. So in total, the area of this right triangle OLC equals to 5R over 2. So the area of triangle OLC also equals to 5R over 2. Minus the area of this sector QOL. So the area of sector QOL equals to pi r squared times 139.632 degrees over 360 degrees. We already found out that the radius of this circle that contains sector QOL, the radius R, equals to 1.907 units in its length. So we substitute R in this equation by 9.107. So R squared is 9.107 squared. So So pi r squared in total is equals to pi times 1.107 squared times 139.632 degrees over 360 degrees. 5r over 2 plus 5r over 2 is 5r. In total, the value of this expression is equal to 4.387 squared in size. So total, actually found out that the area of the green shape equals to 5r minus 4.387 squared in size. R is 1.907, therefore 5r is 5 times 1.907, that is actually 9.535. In total, the area of the green shape equals to 9.535 minus 4.87, that is equals to 5.148 squared in size. So she found out that the area that we're looking for this question, that is the area of the green shape, in total it is equal to 5.148 squared in size. So we finished with the first question. In the next step, I presented to you the second question, and we solved the second question by using 3 different methods. So repeat on all the 3 methods. Our task in the second question was to find out the area of this square ABCD. So the drawing of square ABCD, this is diagonal DB of square ABCD. This is again the BDC, this was BDQ, this was to 30 degrees in size. This is again QBC, this is also equal to 30 degrees in size. This is line side PB, this is equal to 5 degrees in its length. Again, our task is to find out the area, of this square ABCD. So we repeat on the first method. So the diagonal DB bisects square ABCD. So the first half is 45 degrees, and the second half is also 45 degrees. But this angle equals to 30 degrees, and the missing angle must equal to 15 degrees in its size. Likewise, diagonal BD bisects angle ADC. So the first half is 45 degrees, and the second half is also 40. This is second half, this is also equal to 45 degrees in its size. But this angle equals to 30 degrees, and therefore the missing angle must equal to 15 degrees in its size. So in the next step, so actually in this triangle DBP, this angle equals to 30 degrees, this angle equals to 15 degrees. 30 degrees plus 15 degrees is 45 degrees, and therefore this missing third angle must be equal to 125 degrees inside, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we did the construction, that is to say, from the vertex C of square ABCD, we drew angle bisector of this angle DCB. So this is an angle bisector. Therefore, this angle equals to 45 degrees, and this angle also equals to 45 degrees, because the angle bisector bisects angle DCB. In the next step, we extended line segment DP by sideline until it touches the angle bisector. We define the touching point of the extended line segment DP with this angle bisector. This point is point Q. So by doing this construction, we created triangle DQC. The triangle DQC, this angle equals to 15 degrees, this angle equals to 45 degrees. 15 degrees plus 45 degrees is 60 degrees. And therefore this angle must be equal to 20 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we join points B and Q together by side line. By joining points B and Q, we get a triangle BQC. In triangle BQC, this angle equals to 15 degrees, this angle equals to 45 degrees. 15 degrees plus 45 degrees is 60 degrees, and therefore this pelvis angle must be equal to 120 degrees, and its side, according to the sum, that says that the sum of the angles in the triangle is equal to 180 degrees. Actually, DQ is definitely a straight line. Why DQ is a straight line? Because we extended the straight line DP by straight line. When you extend the straight line by straight line, the result DQ must be also a straight line. So DQ is a straight line. If you focus on the right side of the straight line DQ at point P, here the sum of the angles must be equal to 180 degrees, according to rule 3, that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line DQ at point P? We have this angle is equal to 135 degrees, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees, according to rule 3. Therefore, this missing angle must be equal to 45 degrees in its size. 45 degrees plus 135 degrees is 180 degrees. That is the sum of the angles on one side of a straight line. So this missing angle equals to 45 degrees in its size. So in the next step, we proved that those two triangles can go into each other according to side angle side rule. So why those two triangles, that is to say triangle DQC can go into this triangle BQC according to side angle side rule. So why those two triangles can go into each other? First of all, DC equals to CB, they are both the sides of a square, therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees, and therefore they are equal to each other. And finally, QC is the common side that belongs to both triangles, so we can write down that QC equals to itself is the common side that belongs to both triangles. So in total, we found out that those two sides and the angle that is included between those two sides in this triangle BQC are corresponding equal to those two sides, and the angle that is included between those two sides in this triangle DQC, and therefore those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that those two corresponding angles must be also equal to each other in their sizes. But this angle equals to 15 degrees, and therefore the corresponding angle must be equal to 15 degrees in its size. So in triangle BQC, 45 degrees plus 15 degrees is 60 degrees. Therefore, this missing must be equal to 180 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Likewise, in this triangle PQB, 45 degrees plus 15 degrees is 60 degrees, and therefore this missing must be equal to 120 degrees in its size. So, around point Q, we have three angles. Each of them is equal to 120 degrees in its size. So in the next step, we proved that those two triangles can go into each other according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 45 degrees, and therefore they are equal to each other. Those two angles are both equal to 120 degrees, and therefore they are equal to each other. QB is a common side that belongs to both triangles. QB is definitely belongs to triangle QBP, and QB is definitely belongs to triangle QBC. So QB is a common side that belongs to both triangles, and those triangles are both equal to 15 degrees, and therefore they are equal to each other. So if you found out that those two angles and the side that is included between those two angles, that is side QB, in triangle QBC are corresponding equal to those two angles, and the side that is included between those two angles is also side QB in triangle PQB. Therefore, those two triangles can go into each other according to angle, side angle rule. We have those two angles, and the side is included within those two angles in triangle. This triangle QBC corresponding equal to those two angles, and the side that is included within those two angles, that is also side QB, this triangle PQB. Therefore, those two triangles can go into each other according to angle, side angle rule. And from the fact that those two triangles can go into each other, we derive that their corresponding sides must be also equal to each other in their lengths. Side PB is the corresponding side of side BC. Why? Because in triangle PQB, side PB is located in front. This angle is equals to 120 degrees in size. Likewise, in triangle PQC, side BC is located in front of this angle, that is also equals to 120 degrees in size. So, according to the rule, the corresponding sides can go in triangles are equal to each other. So, those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. So, BP equals to BC. It again, as we found out that PB equals to BC. But it is given us the question that PB equals to 5. So we can either know that PB equals to 5, and from this equation 5 equals to PB equals to BC, we derive that BC also equals to 5. Those two sides of the equation are equal to each other. So BC equals to 5. BC equals to 5. So one side of square ABCD equals to 5 units in incident. Our task is to find out the of this square for ABCD. Actually, we know that the of any square equals to the length of one side squared. This is to say it is the length of side BC of square ABCD squared. BC is 5, and therefore BC squared is 5 squared, that is 25. So in total, we found out that the of this square ABCD, it is equal to 25 square units in its size. We finish with the first method. In the next step, I'll click on the second method. Diagonal DB bisect angle ABC. This is the first half of angle ABC. This is equal to 45 degrees in size. This is the second half of angle ABC. That is also equal to 45 degrees in size. But this angle equals to 30 degrees, and therefore the ABC angle must be equal to 15 degrees in size. Likewise, diagonal BD bisect angle ADC. This is the first half of angle ADC. That is equal to 45 degrees in size. This is the second half of angle ADC. It must be also equal to 35 degrees inside. But this angle equals to 30 degrees, and therefore this piece angle must be equal to 15 degrees in size. So, in triangle DBP, 30 degrees plus 15 degrees is 45 degrees. Therefore, this third piece angle must be equal to 135 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, we did a construction, that is to say, we draw a circle around square ABCD in such a way that point A will be the center of the circle that we will draw, and one side, the length of square ABCD, will be the radius of the circle that we will draw. So AD is the radius of the circle. We define AD as x, so therefore AB is also x. So the radius of the circle equals to x, and x is the length of one side of square ABCD. A is the center of the circle that we will draw. This is the circle that we draw around square ABCD. Repeat again, that point A is the center of the circle. AB is the radius, is equal to x. AD is also the radius, is equal to x. So AB is the radius of the circle. The radius of any circle has two edges. the first edge of any radius must be located on the center of the circle, that is point A, while the second edge of any radius must be located on the circle itself, because this is the definition of a radius. This is the definition of any radius. The first edge of any radius must be located on the center of the circle, while the second edge of any radius must be located on the circle itself. Therefore, point B is located on the circle itself. So the circle passes through point B. Likewise, AD is also the radius of the circle. The radius of any circle has two edges. The first edge A must be located on the center of the circle, that is point A, while the second edge of radius AD must be located on the circle itself. This is the definition of any radius. Therefore, point D must be located on the circle itself. So in total, we should find out that the circle passes from points B and D. So we know that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point A must be equal to 360 degrees. This is a right angle, therefore this angle must be equal to 270 degrees in size, because 270 degrees plus 90 degrees, it is 360 degrees. That is the sum of the angles around any point. So this is center angle DAB is equal to 270 degrees in its size, and it's obtained on chord DB. Repeat again, center angle DAB equals to 270 degrees in its size, and it's obtained on chord DB. Likewise, this is angle DBP. So we found out that angle DBP equals to 135 degrees in size. Is equal to 135 degrees in size, and it is subset on the same chord called DB. So those two angles are both subset on the same chord called DB. Okay, so center angle DB equals to 220 degrees, while this angle DBP equals to half of the center angle DAB. It is 270 degrees over 2 is 135 degrees. Actually, center angle DAB, angle DBP obeys to rule 13. Let's click on rule 13. According to rule 13, a center angle is twice as large as the peripheral angle subtended on the same chord. The drawing circle, this is peripheral angle ACB, it is equal to theta degrees in its size. While this is center angle OB, that's obtained on the same chord AB, exactly like peripheral angle ACB. So those two angles are both subset on the same chord called AB. And according to this rule 13, the size of center angle OB must be twice as large as the size of peripheral angle ACB that's obtained on the same chord. The size of peripheral angle ACB is theta, and therefore the size of center angle OB must be equal to 2 theta. So can you implement rule 13 in our drawing? Why? Because in our drawing, we have center angle DAB that is equal to 270 degrees in its size, and it's subset on chord DB. Likewise, angle DBP subset on the same chord called DB, and it is equal to 125 degrees in its size. That is to say, center angle DAB is twice as large as peripheral angle DBP, and they are both subset on the same chord called DB. So actually, angle DBP obeys to rule 13, because center angle DAB is twice as large as this angle DBP, and they are both subset on the same chord called DB. So angle DBP obeys to rule 13, because it is half of center angle DAB that's subtended on the same chord called DB. And because of the fact that peripheral angle DB, that angle DBP obeys to rule 13, it must be a peripheral angle. Okay? Otherwise, it will not be equal to 135 degrees in size. So angle DBP obeys to rule 13, and therefore angle DBP must be a peripheral angle. We know that any peripheral angle, all of its three vertices must be located on the circle itself. Vertex D is located on the circle of perpendicular DBP. Vertex B located on the circle. So vertex B must be located on the circle itself because DBP is a peripheral angle. So in total, if you found out that point P is located on the circle, the circle passes from point P. Point A is the center of the circle, point P is the point on the circle itself, therefore AP is the radius of the circle, is equal to x according to our definition. So we have here angle, this is angle ABP. Angle ABP is equal to 45 degrees plus 50 degrees is 60 degrees. So angle ABP in total equals to 60 degrees in its size. In the next step, I copy triangle ABP in a new page and we analyze this triangle ABP. This is triangle ABP that I copied from the original drawing. We already found out that angle ABP equals to 60 degrees in its size. In front of those two equal sides, we have those two angles that must be also equal to each other in the sizes. But this angle equals to 60 degrees, and therefore this missing angle must be also equal to 60 degrees in its size. 60 degrees plus 60 degrees is 120 degrees. Therefore, the missing angle must be equal to 60 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Triangle ABP is three angles that are all equal to 60 degrees in their sizes, and therefore triangle ABP is an equilateral triangle. We know that all the sides of an equilateral triangle are equal to each other. Those two sides are equal to each other. That is to say, AB equals to BP. Triangle ABP, AB equals to PB. But according to what is given as the question, PB equals to 5. So we can write here that PB equals to 5. And from this equation, 5 equals to PB equals to AB. We derive that 5 equals to AB. AB equals to 5. Those two sides of the equation are equal to each other. So AB equals to 5. So the length of one side of square ABCD is 5. AB equals to 5. We know that our test is to find out the area of square ABCD. We know that the area of any square equals to the length of one side squared. So it is AB squared. AB is 5, so AB squared is 5 squared, that is 25. So in conclusion, we actually found out that according to the second method, also the area of this square ABCD is equal to 25 squared in size. So we finished with the second method. In the next step, I'll repeat on the solution of the third method. Diagonal DB bisect angle ABC. This is the first half of angle ABC, that is 45 degrees. This is the second half, that is also 45 degrees. But this angle equals to 40 degrees, and therefore this missing angle must be equal to 15 degrees in its size. So triangle BDP, 15 degrees plus 30 degrees is 45 degrees, and therefore this third missing angle must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we define side AB of square ABCD as x, so AD also equals to x. This is a right angle because ABCD is a square. So in the next step, we implemented the Pythagoras theorem on this triangle DAB, the right triangle DAB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle DAB, DB squared, that is the square of the hypotenuse, must be equal to A square plus AB square. Again, dB square equals to AD square plus AB square. dB is the missing side, so it is so it is dB square equals to AD square. AD is x, so therefore AD square is x square, plus AB square. AB is x, therefore AB square is x square. So in total, dB square equals to x square plus x square, that is 2x square. 2x square, so dB square equals to 2x square. Here we took out of this equation and found out that dB equals to the square root of 2, times the square root of x squared. The square root of x squared is x. So in total dB equals to the square root of 2 times x units in its length. That produces dB equals to the square root of 2 times x units in its length. This given us the question that PB equals to 5. So in the next step we implemented the law of sines in this triangle DBP. What is the law of sines? The law of sines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to 3 units in itself. Side AC equals to B units in itself. Side BC equals to A units in itself. This is angle BAC. This is equals to capital E degrees in its size. This is angle ABC. This is equals to capital B degrees in its size. This is angle ACB. This is equals to capital C degrees in its size. So in this triangle ABC that could be any triangle, the following equation is true according to the law of sines. A over sinus A equals to B over sinus B equals to C over sinus C. Again, A over sinus A equals to B over sinus B equals to C over sinus C. So if you implemented the law of sines, this triangle BDP. According to the law of sines, you get that in this triangle BDP, the following equation is true. The dB over sinus 135 degrees equals to BP over sinus 30 degrees. Okay, again, this is dBP. According to the law of sines, the following equation is true. The dB over sinus 135 degrees equals to BP over sinus 30 degrees. We already found out that dB equals to the square root of 2 times x, and PB is 5. And dB equals to the square root of 2 times x, and PB is 5 according to what is given as the question. Sinus 135 degrees is square root of 2 over 2. Over sinus 30 degrees, that is 1 half. So in total, if you found out that square root of 2 times x over square root of 2 over 2 equals to 5 over 1 half. 5 over 1 half is 10. Here we move 2 to the numerator, square root of 2 to the denominator. In total, if you found out that the value of this expression equals to the square root of 2 times x times 2 over square root of 2 equals to 10. Here square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. So in this side of the equation, we left only with 2x equals to 10. 2x equals to 10. Here we divided this equation by 2, and we found out that x, that is the side length of square ABCD, equals to 10 over 2, that is 5. So one side length, the side length of square ABCD equals to 5 units in its length. Our test is to find out of this square ABCD. Actually, we know that the opening square equals to the length of one side squared. The length of one side is x, so therefore the length of one side squared is x squared. X is 5, so x squared is 5 squared, that is 25. So in total, in all the three methods, we found out that area of this square ABCD is equal to 25 square units in its size. Okay, thank you very much.